All right, so this is what we're looking at for the live session this evening. We're not going to go through the entire lecture at length, but we are going to go through some of the finer points of the lecture, some of the things. If you haven't watched it, it's fine. If you have watched it, there are a couple of things I want to go over a little bit more closely and give everybody the opportunity to ask some questions in the live session before we turn everybody loose. Probably not here much more than about a half an hour or so. Longer if anybody wants it. And then after this, I'm going to post up the next homework session, and that won't be due until Monday night. So 6 days from now, right before midnight. So with that, we've still got a couple more people coming in, but I think we're good to go ahead and start getting rolling. All right, so the third lecture is about the planetary energy budget, which is, a lot of times in science, we've got these very, very large sounding, important sounding names for fairly straightforward concepts. But this is basically energy coming into the planet versus energy going out of the planet. And all the core energy really starts with the sun. I mean, yes, there's some geothermal energy. But basically what we're looking at is the sun getting to the earth, and then what happens once that energy gets here. How does the solar energy interact with the earth as a system? That being the atmosphere, that being lakes, that being land, that being ice, because there's all kinds of different energy. We think about just light and heat, but there's actually a lot of different things that are tied into the electromagnetic spectrum. So we are going to spend a little time going over what the electromagnetic spectrum is, just so you have some kind of base understanding of what electromagnetic radiation means. And with that in mind, and since we're talking about climate, ultimately atmosphere, we'll talk a little bit more about the role of the atmospheric gases in regulating the planetary temperature. So we start with the electromagnetic spectrum, electromagnetic radiation. One of the things I want to remind people is that when we say the word radiation, it's not a big scary word. A lot of times, especially people of my advanced age, we think about radiation, we think about nuclear energy, we think about radiation poisoning. That's a very specific kind of radiation. That's high energy radiation. Sometimes they're called alpha particles. But electromagnetic radiation, or we'll just call it radiation, or EM radiation for short, encompasses a broad value, run of values from long waves to short waves. All right, these shorter waves have very high frequency, so they have very high energy. The longer waves, all right, have much longer frequencies, so longer wavelengths. So as a result, they have a lot less energy. So we don't have to worry so much about things that are at the lower frequencies, the larger wavelength, low frequencies, because they don't get in there and start messing with things. When I say messing with things, when we go back to that term radiation as a catch-all, those low frequencies, high wavelengths, they don't get in and start messing with DNA. They don't start poisoning people, things like that. That's that stuff on the far right part of the screen. Gamma rays, cosmic rays, X-rays, those kinds of things. In the middle is the visible part of the spectrum, what we can see with our eyes. It's a very, very tiny part of the overall electromagnetic spectrum. And then as you go to lower frequencies from visible light, that's where you start running into infrared and then microwaves, ultimately going into radio waves. So your cell phone there is generally microwaves to radio waves, which is why we're not too worried about keeping it too close to your head all the time. Wouldn't make it a habit, but I certainly don't worry about it, because the kind of radiation coming from that is fairly small, fairly benign. This is a closer look at the spectrum, and this is something you can go back and kind of examine as you want to get a sense of of where everything falls on the spectrum. But, the general idea is that we sense stuff with our eyes toward the middle there, the visible light. To the right of that, high energy. To the left of that, low energy. All right, longer wavelengths, shorter wavelengths, higher energy to the left, to the right. um, so gamma rays, X-rays, ultraviolet, and then visible, infrared, microwaves, radio waves. Those are really the main categories that you should be familiar with. Ultraviolet, X-rays, gamma rays, they're higher energy. Infrared, microwaves, radio waves, lower energy. And there's one more of these just for purposes you can look at later on. At the top says ionizing radiation. That's where I talked about the very high energy particles. They can get in there and start messing with molecules and things and atoms, and ultimately they start tearing apart atomic structure and create ions, as opposed to just electrically neutral molecules. All right, so you'll hear the concept of a black body. Black body is a theoretical structure, table, lamp, anything, any kind of piece of matter, all right, that sits at a constant temperature, because all the energy, in this case radiation, incident upon it also leaves it. So there's no reflectivity. It's all absorbed and then all given back. So if you have the same amount of energy coming in as you're giving off, there's no net change in the temperature of that body or that piece of matter. It's a perfect absorber and perfect emitter of radiation. I think there's very few of these that are out there in nature, to be sure, but it gives us a good first approximation to start analyzing or start thinking about how different things react, how different matter, pieces of matter react in different radiation with different forms of radiation. Wien's displacement law, that's another one of these fancy terms, but basically this is kind of intuitive. It says things that are hot emit radiation that peaks at relatively short wavelengths, whereas relatively cold things emit their peak radiation at longer wavelengths. All right, so things like the sun, they send a lot of energy in the visible, but the sun also sends out energy in the infrared. It sends out energy in the ultraviolet, obviously. It sends out radio waves. It actually sends out some X-rays, all right? But where an object is sending out most of that energy, most of that particular wavelength / frequency of energy is dependent on the temperature. All right, so a very hot object is going to be emitting a lot more in the ultraviolet. A relatively cooler object is going to be radiating, if you will, much more in the infrared. All right, and that's based on the temperature. Again, you're getting EM radiation from those objects at all frequencies and wavelengths, but where it peaks is dependent on the temperature. And of course, you have the classic, and I still remember this thing from when I was an undergrad, the Stefan Boltzmann law. The important thing here to remember is that energy isn't directly proportional to temperature. When we think about units of energy and temperature, they're clearly related, but it's not like, well, your temperature goes up 1 or 2 degrees, your energy goes up 1 or 2 units. It doesn't work like that. Energy goes as the 4th power of temperature. And this is absolute temperature, the Kelvin scale, whereas 0 Kelvin is minus 273 degrees Celsius, minus 459 Fahrenheit, where they're all theoretical molecular motion stops. It's as cold as it can get. The background temperature of the universe, I think, is 3 or 4 K. It's cold. I mean, really cold. All right. So in the absolute sense, as you increase the temperature, all right, the amount of energy goes up to the 4th power of that. So basically, a small increase in temperature gives you a big increase in energy. And that's the key relationship to remember there. Thinking about that in reverse is the inverse square law, which means that when you double your distance away from something, you don't lose half of the energy, you lose half squared of that. So in other words, you only have 1/4 of the energy you had previously. All right, so you increase the distance by half, your energy drops to a quarter of what it previously was. So in that bottom one there, if your energy is full on at 100% in position one, you double it to position two, and now you've gone down to 25% of what you had earlier. And it goes down logarithmically from there. All right, so temperature and energy are related, but energy goes up very fast as a function of temperature. But then energy received drops much more rapidly as a function of distance than just linearly. So those are the two big concepts to kind of remember. Not going to get a whole lot about the sun. I mean, there's sunspots, which are relatively cool spots on the sun, and the parts of the sun, the photosphere, chromosphere, corona. They're not awfully important. They're good to know what the corona is. It's not just a nice beer. It's the area of hot gas, ionized gases around the sun, generally not visible except during, to the naked eye here on Earth, except during a full solar eclipse, total solar eclipse, which is, saw that in 2017, which was pretty cool. All right, so some of this stuff might seem familiar from grade school, but how much energy is coming in from the sun to a specific spot depends on the solar altitude, or how high the sun is up in the sky. All right, so that's the classic flashlight analogy. So if the sun is directly overhead, like a flashlight there, all the energy is focused in on that one circle, and it's a very compact area. All right, but let's say we get to winter time for us here in the northern hemisphere, and the sun doesn't get up as high in the sky. The sun's still sending the same energy as it always does, but it's spread out over a larger area. So you're getting less energy per unit area than you were during the summer. This is why things like pavement in July get way, way hotter than pavement does in January. This is why you walk on the beach in July, that sand gets really, really hot. But then 3 hours later, the sun is lower in the sky and the sand isn't as hot anymore, because you've got more energy coming in per unit area on the ground when the sun is higher up in the sky. And this is this gives you another kind of idea from the global aspect. Not only is it the incoming energy to the surface of the Earth a function or go as the angle of the sun in the sky in of itself, but the fact that we do have an atmosphere, that energy has to pass through the atmosphere before it gets down here to the ground. Right? So at the equator, there's less energy, there's less atmosphere to pass through, all right, compared to a higher latitude, 60, 70, 80 degrees north latitude, all right? So the sun is coming, the solar energy is coming in at an angle, and the sun it's coming in and has to pass through more atmosphere before it gets to the ground. So you've got two things working against you, getting energy from the sun all the way to the ground, and that's the top part there. And that's backwards. All right, so remembering a couple of things about the Earth in space that are important. Obviously, the rotation of Earth on its axis accounts for day and night. Be surprised how many people don't know that. But the Earth does not go around the sun in a perfect circle. It's an ellipse. And that ellipse actually varies in its eccentricity very slowly through time, over thousands of years, as does the Earth's axis. Right now, it averages about 23.5 degrees from the vertical, kind of like that. But it does fluctuate between about 22.5 and 24.5, again, over thousands of years. But also during the course of a regular year, the Earth is not wobbling on its axis. It goes around in the axis is going in the same direction as the Earth goes around the sun. And this is basically why we have seasons. Now, back to what I mentioned before about the orbit not being a perfect circle, there are two nicknames we give to that time of the year when the Earth is either closest to the sun in its orbit or farthest from the sun in its orbit. Perihelion, when the Earth is closest, and aphelion, when its Earth is the farthest. And it's not a huge difference, but it is enough. So here's another diagram. The top left there, again, it's the classical Earth going around the sun during the course of the year. To the far left is the winter solstice. The northern hemisphere is tilted away from the sun. And the summer solstice, the northern hemisphere is tilted toward the sun. So back to what we said earlier, in the summer, there's more direct sunlight into the northern hemisphere. For us on the ground, the sun is higher in the sky than it is during the winter. All right. But you could see there also that the Earth's axis is always pointed in the same direction, 23.5 degrees from the vertical. But always in this case, it's just slightly to the left. And then back to the eccentricity of the orbit, it's not a massive difference. During aphelion, it's 94.5 miles. During perihelion, it's 91.4 million miles. Difference of about 3 million miles. All right. And ironically, here in northern hemisphere winter, we're actually closer than we are during the summer. So a little review of some other terms that come around a lot. An equinox is Latin for equal night. Equinox, equal night. Then the sun's noon position, if you will, is directly over the equator. And that's a classic. Everybody on Earth gets 12 hours of daylight and 12 hours of not daylight. All right. The solstice is a time when that tilt is kind of maximized, if you will, with respect to one or the other hemispheres. All right. So during the year, the winter solstice, that's when the northern hemisphere where we are is tilted the most away from the sun. And conversely, in the summer solstice in June, that's when we are tilted the most toward the sun. All right. And so if you think about the lines of latitude around the Earth, the Tropic of Cancer is 23.5 degrees north latitude. And during the first day of summer, the summer solstice, the sun is directly over that point, where the sun would be 90 degrees up in the sky if you were standing at 23.5 degrees north latitude on the first day of summer. First day of winter for us is the first day of summer in the southern hemisphere. So the Tropic of Capricorn, 23.5 degrees south latitude, all right, on December 21st, 22nd, the sun is 90 degrees overhead. And again, the same concept here. Arctic Circle, Antarctic Circle, equator. By the way, the Antarctic Circle and the Arctic Circle, you subtract off the 23.5 degrees from 90, and that's where you get the latitudes of those. So the Arctic Circle, 66.5 degrees north, Antarctic Circle, 66.5 degrees south. And the times you see there kind of going around the globe show you how much daylight is getting in a 24-hour period during the summer solstice. So the equator is always getting 12 hours, okay? But at the North Pole, during the summer solstice, the sun doesn't set. Conversely, during the summer solstice, June 21st, the South Pole doesn't get any sunlight at all day long, at all. Sun doesn't even come up. And it's like that for weeks at a time. But during the summer solstice, someplace like Virginia, Pennsylvania, we're doing about 13, 14 hours of daylight during the first day of summer. And it's reversed during the first day of winter. All right. So as a result, it kind of makes sense. This kind of sums it up. The sun's daily path through the sky changes as the Earth's orientation changes as it goes through the year. Yeah. What the sun would look like in the sky. You can go back and look at that. I talk a little bit more about this in the video. The idea here being Edmonton in Canada, the solid line here, we go January to December, and on the vertical axis is how much daylight you get in a 24-hour period. So in the dead of winter, Edmonton, 54 degrees north, there's not a lot of sun. You get 7 hours of daylight during the 24-hour period. But then as you go marching into the summer, by the summer solstice in June, you got 17 hours of daylight, right? And then it falls back off to 7 by the first day of winter. But Mexico City, Caracas, Venezuela, these places that are close to the equator, there's a small variation, but there's not as much. So they have, through the course of the year, a lot less of a variation in the amount of solar energy getting into their local latitude, their local location. So the temperatures of their seasons do not vary as much. It's generally warm most of the time. The solar constant is not really a constant. That's the funny part, but it's a good working definition of how much energy is getting to Earth from the sun. And the convention follows this way. It's the rate at which solar radiation falls on a unit area of a flat surface located at the outer edge of the atmosphere, perpendicular to the incoming beam at its mean distance from the sun. It's a lot. So basically, when the sun's energy gets to the top of the atmosphere before it starts bumping around with the molecules and diffracted, diffused, reflected, whatever, that's how much energy is getting to the Earth from the sun. So it's a good measurement of how active the sun is. And it doesn't change very much. That's why it's called the constant. There are small fluctuations depending on if the sun is going through a relatively cooler or relatively more active period. It's generally about 1,366 watts per square meter. And sometimes it's 62, sometimes 68, but it generally holds in that ballpark. So for every square meter, that's a lot of energy per square meter that is getting to the Earth from the sun. Think about a 100-watt light bulb, all right, put that over top of a square meter, or take a yardstick in two directions and put a light bulb on it, a 100-watt light bulb, all right, and then you multiply that by 13 or 14 per square meter. So it's a lot. This is just another example, another way to look at how the solar energy is getting to different places on the Earth. We've kind of taken the classic globe and flattened it out. So what I mean by that here on the graph, on the right, on the vertical, here's the latitude in degrees, with the 0 being the equator. Down here, -90 is the South Pole, 90 here's the North Pole, and then day of the year. So this is January through December. So like we said at the outset, down here at the bottom, -90 is the South Pole. In January, the sun is up all day long. And then by June, the sun isn't up at all. And the reverse is true at the North Pole. In January, sun is not out at all, but it doesn't set in June. All right. And so each place on the Earth's surface with latitude that varies through the course of the year. And this little thing called the subsolar point is the idea of where the sun would be 90 degrees up in the sky. All right, so during the beginning of winter, our winter, there it is about -23.5, it's Tropic of Capricorn. All right, so the sun is directly over that latitude point. All right, and then right here, it crosses the 0 point here. That's going to be your equinox right here and right here. And then there's the summer solstice for us right there. All right, so that's the sun getting to the Earth. So then what happens once that energy gets here? A lot of things happen to it. Scattering and reflection. Scattering means that the energy is hitting something and it starts literally scattering in all directions, whereas opposed to reflection means that it's taking place at the interface, at the molecular level, anywhere between different kinds of reflective medium. And then some of it is scattered backwards. So basically, reflection is like scattering, except scattering back in the direction in which the energy came from. And that fraction of radiation that is backscattered or reflected is known as the albedo. That's a very, very important word in climate circles, albedo. High albedo things send back a lot of energy. They're very reflective. Low albedo, low reflectivity things absorb a lot more energy. It's a picture I took years ago, but it's a little, it shows a little bit about what we're talking about with the backscattering or forward scattering, because you can forward scatter light too, excuse me. So the one on the left there, and this is, I took this out of my 1980 Oldsmobile back in 1993. So we're looking forward in the car on the left. And pay attention to the trees. It's a dead of winter and it just looks like a bunch of trees with no leaves. All right. But we turned around and looked out the back windshield at exactly the same time. And you could see the trees glistening because there's ice on them. All right. But you couldn't see the ice in the northbound shot. You could see it in the southbound shot. So what's going on here? Sunlight, when it interacts with water, is scattered preferentially forward. I mean, it scatters in all directions, but there is a large component of sunlight scattered forward through water molecules. How we observe that is through those two photos right there. So remembering that I'm driving this car and the sun is behind me. All right. So if the sun is behind me as I'm driving this car, the sun hits the ice, water molecules on those trees, and the light continues to scatter forward in that direction. All right. But the reverse is true. As I look out that back windshield, all right, now I'm looking toward the sun. I'm not looking right into the sun, but I am looking toward the sun in the direction of the sun. So sunlight is hitting the water molecules and the ice on those trees and scattering toward me. So that's why I see it glistening in that southbound shot versus that northbound shot. Okay, so scattering, reflection, absorption also happens. All right, so it can be reflected, backscattered, it can be scattered in all directions, or it can be absorbed. All right, the energy can be absorbed. So this is a conversion of energy where some of that radiation comes in, hits an object, and it's converted to heat energy. All right, it warms the thing up. It warms up the molecules. It gives them higher energy. So we see that with oxygen, ozone, water vapor, and other aerosols that are impacted by incoming solar radiation. Aerosols here, we hear aerosols a lot. We think about spray cans. An aerosol, when we're talking about climate, when we talk about weather, is anything that is up in the atmosphere that is suspended. It could be dust particles. It could be salt. It could be volcanic ash. And normally it's not that much of it. You can't see it. But any kind of liquid or solid, small particle that is suspended in the air is called an aerosol. And again, those can absorb solar radiation as well. But the absorption by the gases in the atmosphere depends on the wavelength of the incoming radiation. And man, that gets messy, although we do have to address that. So first, let's talk about ozone. There is, you probably remember this from grade school. Ozone absorbs ultraviolet radiation so we can all run around outside and not get fried. And that's for the most part true. The greatest concentration of ozone, which is O3, it's 3 oxygen atoms and bound together, is up about 25 miles in the stratosphere. In fact, that's why temperatures rise as you go into the stratosphere, because you've got all this ozone being created and destroyed at the same time, what we call steady state reactions. All right, so the chemical reactions involved in formation and the dissociation of ozone is what's driving the temperature rise in the stratosphere. And it doesn't absorb all the ultraviolet radiation. It absorbs most of it, the highest energy ultraviolet radiation. That's why you still get sunburned in the summer, because some UV is getting through. So here's a little schematic just to give you an idea how ozone is produced and then ultimately destroyed, disassociated, whatever. And my chemistry here isn't as strong as I might like, but just kind of go with me for a minute. You've got high energy UV, ultraviolet, striking an oxygen molecule, the classic O2, all right, and cause it to split into 2 oxygen atoms. And then those freer singular oxygen atoms will collide with other O2, molecular oxygen, and then form ozone. But at the same time, you've got new ozone running around, O3s, all right, and then they absorb some UV radiation that will split the molecule into one atom and then another piece of diatomic or molecular oxygen, O2. All right, and then that free oxygen atom can collide with another ozone molecule and then form two molecules of oxygen. So these things are kind of going on back and forth all the time, but in the net, there's not a big change in the amount of ozone up in the ozone layer in the stratosphere. Again, 25 miles up. We love ozone 25 miles up. The problem with ozone close to the ground where we live, and it's not prevalent at all, except during the summertime, we can get ozone forming from, emissions from industrial emissions, automobiles. Some of the emissions interact with ultraviolet and we get ozone formation. And that sounds great and all, but ozone is actually caustic to your lungs. That's not something you want to be breathing in. It's great up there, but we don't want it down here. All right, but it tends to go away after the sun goes down because it really depends on ultraviolet radiation getting through. That's why it's not too big of a problem here at the ground level during the dead of winter, as opposed to summertime where there's more UV getting in here anyway because the sun is higher up in the sky. So the ozone hole that you probably heard about, this was a much bigger deal many years ago when NASA scientists discovered that there was a massive drop in the concentration of ozone in the stratosphere around the South Pole. At first, they were like, this can't be right. These numbers are way, way too low. And then after a lot of research, the scientific community discovered that chemical propellants in aerosol cans, chlorofluorocarbons that were in there, refrigerants also, chlorofluorocarbons, that were thought decades and decades ago to be fairly innocuous, were actually, as they escaped ultimately into the atmosphere, they were taking out ozone. And most of the time it was in the coldest part of the Earth, and that being over the South Pole, because you need to have other chemicals in place to start taking out the ozone, if you will, and taking out the ozone tends to happen at very, very low temperatures. So in the polar night, if you will, that's when we start to see the biggest decreases in ozone concentration over the South Pole. So on that graph, you see that the ozone was dropping a lot from the end of the 1970s through about 1992, 1993, because in 1987, the nations of this earth got together and listened to the scientists who said, we need to stop making this stuff because if we keep putting these CFCs up into the sky, they're going to continue to start eating away at the ozone in the stratosphere, not just the poles, but that's going to start to work its way globally. And then you're going to have way more UV getting all the way down to the ground. And we wouldn't all fry in 10 or 15 years, but it is going to increase incidences of things like cataracts, skin cancer, and stuff like that. And then it would get worse over time. So with the Montreal protocols in place, the level of ozone stabilized, if you will. That's why you see this kind of flat part of this trend line from the early 90s through about 2010. And now we're beginning to see a little bit of an uptick. And this is an older graph. I couldn't find one the last 2 or 3 years. But the ozone hole, if you will, is starting to slowly repair itself. And to be fair, it's not entirely a hole. It is just a massive, massive drop. I mean, and that's what you see there. The number went down to what's called Dobson units. So it's a measurement of how much ozone is in the atmosphere. And so it dropped, but now it is stabilized, and it's going to slowly start to work its way back. So that's a good sign. So talked a little bit about the solar radiation getting to the ground, direct solar radiation, that flashlight basically lighting up the surface, direct solar radiation getting to the ground. So we get shadows. You get shadows from direct solar radiation. The sun is out. You can see it when you're outside. Diffuse solar radiation is scattered or reflected to the Earth's surface. So think about a cloudy day where you're outside and you can certainly see, but there's no shadows. So what you're getting is diffuse solar radiation, right? The sunlight is hitting the clouds, bouncing all over the place, and some of it is obviously going back down to the ground. And there's plenty out there still to see what you're doing. But that's why when you get under a very, very tall cloud, like a thunderstorm cloud that goes up 6-7 miles up into the sky, it gets dark during the daytime because the sun has to go through a lot more water in that cloud to get down to the surface. But why most of the time, if you just have some clouds out, it's not awfully dark outside. So when you add up the direct plus the diffuse solar radiation getting the Earth's surface, how much hangs out at the surface or gets through the surface, reflected or absorbed, depends on the surface albedo. All right, so the albedo is also a measure of diffuse radiation, not just direct radiation. So in other words, snow is still bright even on a cloudy day because it has a high albedo. And we won't go through this one a whole lot. This gives you just some ideas about what types of surfaces and kind of what albedos they have. You know, fresh snow, very high, 75 to 95% reflective, but forests, very, very low. You know, they're dark green, there's soil, there's vegetation. They're taking in a lot of energy, whereas snow, ice reflects a lot of energy. With regard to water and albedo, there's some interesting things going on there because it depends on the angle of the sun and water. So, for example, water absorbs, let's start with this, water absorbs longer wavelengths of light more than shorter wavelengths. So if you think about, you know, white light consists of all the colors in the rainbow. As the sunlight gets to the ocean, the reds and oranges get absorbed first. So with those getting absorbed, that's left with the blues and greens. So that's why we end up seeing kind of this blue-green color to the ocean when, you know, it's not polluted. So that's the bottom part. The visible solar radiation is selectively absorbed by wavelength as it goes through the ocean. In other words, these higher wavelengths get absorbed, and what's left are these lower wavelengths down here, and they go a lot deeper before they're absorbed. The albedo of a flat, undisturbed water surface, again, assuming a clear sky, changes with increasing solar altitude. All right, so as the sun gets higher in the sky, all right, the albedo drops. So after lots of calculations, lots of experimental studies and all these things, the general idea for how much solar radiation is getting to the Earth kind of plays out this way. Reflected by the Earth atmosphere system, 31%. 20% absorbed by the atmosphere, and about half of it is absorbed by the Earth's surface. So thinking about the solar energy that gets to Earth, 20% is absorbed by the atmosphere, and about half is absorbed by the Earth's surface. The rest is reflected. So you've got reflected or absorbed. So there is more absorbed than there is reflected. And this just, I'm not going to get into this a whole lot because the thing to remember here, this kind of weird graphic, is that the sun doesn't heat the air much. I mean, it does. Obviously, as we just saw, the sun does, the atmosphere does absorb some solar radiation, but for the most part, the sun heats the ground. There's a lot more absorption of solar radiation going on at the ground, right? So the sun heats the ground, and the ground actually heats the atmosphere from below. And that's sometimes hard to wrap your head around at first, but it's responsible for the daily fluctuation in the temperatures. So back to the original point, the outset, the global radiative equilibrium, the black body, whatever, outgoing emission of heat to space in the form of infrared radiation is balanced by the incoming solar radiation coming into the Earth. All right, so if the temperature doesn't change on the global system, what the Earth is giving off in the infrared is balanced by the energy coming in from the sun. So when the temperature doesn't change, we say it's in equilibrium. The greenhouse effect in the atmosphere is a little bit different than how a greenhouse actually works. So for atmospheric purposes, the greenhouse effect is a heating of the Earth's surface and lower atmosphere caused by strong absorption and emission of infrared by certain atmospheric gases. Things like water vapor, carbon dioxide, methane. These are gases. There's not that much of these gases around, but they absorb a lot in the infrared part of the spectrum. A lot. They really go a long way in kind of regulating the temperature of the Earth. All right. So the sun comes down, warms the Earth, and the energy from the Earth's surface goes into the atmosphere. And that's largely going off in infrared parts of the spectrum coming from the Earth. Earth mostly gives off in the infrared. But the gases that envelop the Earth, there are small amounts of these gases, greenhouse gases, all right, that are very good at absorbing stuff in the infrared and then sending it back in all directions out to space and then back down to Earth. So those are the greenhouse gases. Sometimes we'll call them, when we geek out, we'll call them infrared active gases, because they absorb a lot in the infrared part of the spectrum, what we think is the warm or the heating part of the spectrum, right? An actual greenhouse works a little bit differently. That's more of literally trapping heat. Sun comes through the greenhouse, heats the surface, and it warms, and there's no convection. There's no way for the air to get out because you've got things closed up, all right? It's similar, but not exactly the same, but it's close enough where the term is stuck. So there's the actual greenhouse at the top, and the absorption spectrum there is at the bottom. I'm going to get back to that one in a minute because that's one I really want to go over. So the greenhouse gases, water vapor, CO2, ozone, methanes, and nitrous oxides. Those are the most important ones. All right. Water vapor and CO2 for our purposes really lead the pack. Now, I went through this a lot in the recorded lecture. I want to go through this again because this is ugly. I mean, it's ugly. I'm not going to pretend it's that ugly, but work with me here for a minute. All right. So down here at the bottom, we've got this little part of the electromagnetic spectrum. All right. There's this visible part, and this is the wavelength. It's in micrometers, microns. Basically, what's the wavelength of these waves? So visible is down here, 0.4 to about 0.8, all right? Then you've got over here toward the right, you've got higher values, which are in the infrared. So this is kind of flipped from what we had directionally earlier in the lecture. So you've got lower energy to the right here in infrared. You've got higher energy ultraviolet here to the left, all right? So we've got ultraviolet to visible to infrared. Now, each one of these slices represents a certain gas in the atmosphere. And then this bottom slice here represents the atmosphere as a whole, summing up all of these other ones. All right, so let's start with this purple stuff over here. Ultraviolet. This is to the left of the visible. This is ultraviolet radiation, okay? So all this is 0 to 1, which is, if it's at 0, that means it's transmissive. All of that wavelength is getting through. If it's one, that means it's all getting absorbed, right? So, for example, here O2 and O3, oxygen and ozone, ultraviolet. This is all filled in. This is telling us that basically oxygen, and especially ozone here, is absorbing almost all of the UV. Okay, so water vapor is not absorbing any UV. Carbon dioxide is not absorbing any UV. Nitrous oxide is not absorbing any UV. Methane is not absorbing any UV. Oxygen and ozone, they're doing all the work here. So when you add that up, sure enough, for the atmosphere as a whole, UV doesn't get through, at least as much as it would otherwise. Most of it's absorbed. Most of it's absorbed. This is called a visible window, which is kind of makes sense. The gases in the atmosphere aren't absorbing a lot of visible light, a tiny bit, but not much. You know, methane doesn't absorb visible light, neither does nitrogen, nitrous oxides, CO2, water vapor. Oxygen does a little bit, not a lot. So this is why we can see, because light, as we know it, visible light goes through the atmosphere. Now we go to the infrared part of the spectrum, and it gets ugly. It gets really complicated. All right. In the near infrared and then the farther infrared, you have these different bands that are absorbed differently. Okay. So water vapor here is absorbing kind of half here at 1 micrometer. It's absorbing almost everything at about 1.8 micrometers. Absorbs almost everything between 2 and 3 micrometers. This is all infrared. All right. There's near infrared and far infrared. All right. Then once you get past about 15, the atmosphere is pretty much opaque or to the infrared. All right. And it's not kind of colored in here because we've just labeled the gases. We're just putting the labels here. All right. But water vapor, again, we're talking about green. These are greenhouse gases. Water vapor, carbon dioxide. These big peaks are showing you, yes, they're doing a lot of work absorbing in the infrared part of the spectrum. All right. There's a little going on with oxygen. There's a little going on with nitrogen dioxide. Excuse me, nitrous oxide, not dioxide, nitrous oxide. And methane, CH4. All right. So all these little peaks are showing you where there's absorption of gases, absorption of infrared energy by gases in the atmosphere. Sum it all up and you get down at the bottom. So you see a couple of these places where the 8 and the 10 are with the little IR windows. There are a few places in the infrared that are transmissive, highly transmissive in the infrared. All right. There's not a lot, but there are a few. That's why they're called windows. They're not a lot. They're small, but there are a couple small frequencies in the infrared where the energy can get through. And those frequencies are what we tune our satellites to, so we can try to figure out where clouds are from space in the middle of the night. If you send your satellite up and tell it, hey, I want you to look for stuff that's 30 micrometers, it's going to just laugh at you. All right. But if you set up your detectors and your satellites to look for energy coming off of the Earth, running between 8 micrometers, another one like 10, 11 micrometers, you'll be able to see the stuff that's on the Earth, the energy that's given off from the Earth, makes it all the way through the atmosphere into space. Then can be detected by the satellites in orbit. And I just think that's fascinating. That's a complicated graph, but there is a lot of really good information going on in that graph. All right. And this just kind of emphasizes the point. Water vapor strongly absorbs in the outgoing IR and emits back in the Earth's surface. The greenhouse gases don't instigate the warming. They're not creating the warming. They're absorbing and then sending it back in all directions. Right? They're absorbing terrestrial infrared, stuff that's coming off of the ground, going back into the atmosphere. Those gases are absorbing that energy and emitting it in all directions. And one of those directions is back down to the ground. This is also one of the reasons why, all else being equal, in the dead of winter, it is warmer on a cloudy night than it is a clear night. Why? Clouds are made out of water. Water is, it's most, no, clouds are liquid water, but there is also water vapor interspersed within the water droplets. So they are sending energy back down to the earth. Like last night here in Pennsylvania, it got down to 15 degrees at like 10 o'clock. Clouds rolled in 11, 12 o'clock last night, and the temperature went up 7 or 8 degrees. Sun didn't come up, clouds rolled in. It effectively helped warm us up in the middle of the night. Not an awful lot, but enough. The first person in modern meteorology to really postulate or come up with this idea that, you burn enough fossil fuels, you're going to change the climate, was Guy Callender, British guy. He wasn't the first person to discover the greenhouse effect. That was actually discovered by several other scientists 100 years before him. But he's largely given credit for the idea of transforming the climate. Now, when we look at the relative importance of these greenhouse gases since the late 1970s, you hear CO2 all the time. This is why. When we look at how much radiative forcing, or basically how much energy the gases are providing back down to the surface, what is each one's role in the greenhouse effect? All right, because we keep pumping CO2 into the atmosphere and it doesn't go anywhere once it's up there, that continues to rise. That's that light blue bar. Back in the 1970s to 2020, that's risen watts per square meter, from about 1 to almost 2 additional watts per square meter. Whereas you see nitrous oxide, CFCs, methanes, they haven't changed as much because there's so much more CO2 than those other gases. Methane is actually a stronger greenhouse gas per molecule than CO2, but there's just so much more CO2 that's out there. You might have heard concern about these things called methane bombs. Oh my gosh, we're going to melt the permafrost and all this methane is going to get loose. And that might happen, but methane naturally returns back to the ground a lot more quickly than carbon dioxide does. So the problem is that it will be emitted far faster than it will settle back out out of the atmosphere and in the ground. This is the classic Keeling curve. Charles David Keeling came up with this in the late 50s. Callender did all of his research, and then Keeling and Mauna Loa in Hawaii started actually monitoring CO2. This is the first place to actually monitor how much CO2 was in the atmosphere. Our data from before that regarding CO2 comes from the paleoclimate records, which we'll talk about in a couple more courses. All right, but this is physical, how much CO2 is in the atmosphere. And the reason this was done out in Hawaii is because, for the most part, on a big mountain in Hawaii, you're away from urbanization. You're away from North America. You're away from Asia, these big manufacturing centers where you're just pumping pollution, into the atmosphere. So this is giving you a better representation of how carbon dioxide is well mixed through the atmosphere. When you stick your CO2 detector next to a smokestack in South Philly, it's going to register a lot differently. All right. But what we've seen is since 1957, there is a rapid increase in the global concentration of carbon dioxide. And yes, Virginia, it's from the burning of fossil fuels. It's not volcanoes. It's not people exhaling. It's the burning of fossil fuels. You see a tiny little sawtooth pattern to that curve. The black line's the average. The red line's the actual measurements. There's little ups and downs every year because when springtime comes and the trees all leaf out, they're going to start taking in more CO2. So the CO2 level drops a tiny bit. But then in the fall, all the leaves fall off, and the CO2 basically gets re-released into the atmosphere. So there's a tiny annual fluctuation in the amount of CO2, but in the long term, that little annual fluctuation is just squashed by that longer term black line there. Yeah. There's a lot of CO2. I just talked about that. We're heating things up. So that's basically it um, for tonight. So, the take home message: different external and internal forcing will lead to a new average equilibrium temperature of the planet, right? So if the planet were in balance, if you will, the amount of outgoing energy from the Earth system, outgoing infrared, matches the incoming solar, all right? But if you start changing forcings, whether inside the system or outside the system, you're going to send the temperature of the planet to a different equilibrium. You start increasing greenhouse gases, you're changing the internal forcing of the planet, so you're going to raise the temperature. The sun starts to get suddenly hotter. Oh, that's an outside force. That's going to change the temperature of the planet. There have been periods several hundred years ago where the sun was relatively cool. There was a big lack of sunspots. Um, so the solar constant dropped a little bit. So the planet cooled for a little while, a tiny bit for a little while. All right. Um, so as those forces change from the outside or inside, it will change the overall temperature of the planet. So that's the big message to take home here. We've got solar, we've got infrared, understand the EM spectrum, understand the difference between ultraviolet and infrared, understand the difference between X-rays, radio waves, understand why radio waves aren't going to mess around with your DNA, but you'll want to be near gamma rays because that's a bad scene. So that's a quick version. So next time, we'll talk about the thermal response to the climate system, basically how heat moves around the planet. So now we've got an idea of the general temperature of the planet, but we haven't talked a lot about why this part is hotter, this part's cooler with regard to land, oceans, uh, air circulation, ocean circulation. Those are the things that we will do next time. So that's it. If anybody's got any questions and they want to scream, holler, raise your hand, whatever, I can hit them now. Otherwise, everybody's free to go. And I'm going to post a new homework set later on this evening, but that won't be due until Monday night. So is everybody good? Anybody got anything? Going once? Going twice? All right. Take care, everybody. We'll see you next time.